Okay, so next we want to know what happens when you apply a torque to an object. So in a lot of ways, this is just like the second law for linear motion. So there, the force is equal to the mass times the acceleration. And so for a rotational motion, the torque is equal to the moment of inertia times the angular acceleration. So the torque here is analogous to force, the moment of inertia is analogous to mass, and the angular acceleration is analogous to regular acceleration. So let's look at what's happening here. So we are looking down on a rotating wheel that is spinning counterclockwise. If we use our first version of the right-hand rule and wrap our fingers around the axis with our fingers going counterclockwise, and that then means that the angular velocity vector is pointing out of the page. So we are applying a force that is also pointing counterclockwise, so our first guess would be that we'd expect the angular velocity to increase. To check this, we can use the right-hand rule for torque, and our index finger here is pointing up and to the right. Our middle finger, so the force is pointing up and to the left, and that then means that our thumb is pointing out of the page. So that means the torque is pointing out of the page, as is the angular velocity. So if the angular velocity and the torque, which is also the direction of the angular acceleration, they are both pointing in the same direction. So if the torque and angular velocity are pointing in the same direction, then the rotation should speed up, just how if you have a force and the velocity are pointing in the same direction, then the object should speed up. If the force was applied in the opposite direction, so clockwise, then the torque would point into the page, or into the screen, I guess, and the angular velocity would point out of the page. So the angular velocity should become slower, because the angular acceleration and the angular velocity are in opposite directions. This problem can be flipped around, so you could be told the direction of the angular velocity and that the angular velocity is increasing. If you know those two things, then the angular acceleration must be in the same direction as the angular velocity, so the torque must be in the same direction. So that's kind of what it's showing on the right here. So that's showing that the angular velocity is pointing up, the angular acceleration is pointing up, so then that means that the torque must be pointing up as well. Okay, so let's look at a problem. We have two rotating disks here that have the same mass, but disk number 3 has 3 times the radius of wheel number 1. So if the same force is applied as shown, then what is the relationship between the angular acceleration, alpha 1, and alpha 2 of the wheels? Alright, so there are two things to keep in mind here. So how does the torque change, and how does the moment of inertia change? So first let's consider the torque. So the torque is the lever arm across the force. So the lever arm of the wheel 2 is 3 times larger than wheel 1. The forces are the same, and the angles are the same. So the torque on wheel 2 must be 3 times larger than the torque on wheel 1. Well, what about moment of inertia? Well, the masses are the same, but the moment of inertia depends on the distribution of the masses. So the moment of inertia is 1/2 mr squared for disks and cylinders, and so the mass of these are each the same. However, the radii are different. So that means the moment of inertia is 3r squared larger in wheel 2 than wheel 1. So when you do that, 3r squared, that becomes 9r squared. So the moment of inertia is 9 times larger for wheel 2 than it is for wheel 1. So that means it's 9 times harder to angularly accelerate wheel number 2, and the torque is only 3 times larger. So that means that the angular acceleration for wheel 2 is 1/3 of the acceleration of wheel 1. Notice that this is a little unintuitive, so the moment of inertia increases with the square of the radius, while the torque increases with the radius, so the moment of inertia increases more. So that's why if you're trying to balance yourself, a long bar or something makes it a little easier, because your moment of inertia increases by a lot, and so that means that the angular acceleration of your rotation becomes smaller, making it, making you a little more stable, making it easier to adjust your balance. Okay, So you have, I guess, a couple questions here that are pretty similar to this one about applying a torque and using this analogy between force and torque. That's it for this week's classwork, so I guess finish off this last question, and good luck and take care of yourselves.